Okay, today we're looking at a paper that's making some serious waves. It's called Rethinking the Trust Region in LLM Reinforcement Learning. It's a preprint from Penghui Qi, Wei Sun Li, and the teams at CAI Lab and NUS.
And they came out swinging. Their core claim is that PPO, the algorithm that's basically the backbone of the entire RLHF industry, is just mathematically broken for large language models.
Yeah, it's a huge claim. They argue that PPO's classic ratio clipping mechanism, which, works great for things like robotics, just completely falls apart when you apply it to the massive vocabularies of LLMs.
It really does. The ratio becomes this super noisy estimate. So what happens is it way over-penalizes updates on rare tokens, which just kills your model's ability to explore.
And at the same time, it under-penalizes these huge catastrophic shifts in common tokens, which is what leads to all that instability we see.
Exactly. So their solution is something they call DPPO, which stands for Divergence Proximal Policy Optimization. And instead of that messy ratio clipping, they constrain the actual mathematical divergence of the policy.
And they use this clever trick to make it efficient, a binary approximation, where they basically collapse the entire vocabulary down to the token we pick versus, well, everything else.
It sounds like a total hack, but it works. On really tough math benchmarks like Amy 24 and 25, it just blows past PPO and GRPO.
Yeah.
And it's more stable and even more computationally efficient.
It's a fascinating paper. It almost suggests we've been fighting our own tools for the last few years without even realizing it.
I think that's the main takeaway.
Okay, so let's dig into that. If you're an ML engineer listening to this, you've probably spent hours tuning a PPO loop. You've got your policy, your reward model, and this idea of a trust region. So why is that suddenly considered broken?
Well, you have to think about what PPO was originally built for. It wasn't designed for, writing poetry or solving complex math problems. It was for continuous control.
Right, like getting a robot to walk. Low-dimensional action spaces, move a joint this way, that way.
Exactly, yeah. And in that world, your policy is usually a simple Gaussian distribution. So checking the ratio between the new probability and the old one is a really cheap and honestly pretty effective way to check, hey, how much did I just change?
The logic being, if the ratio is close to 1, I didn't move much. If it's, say, 5, I moved a lot.
That's the heuristic, yeah. But an LLM is a totally different animal. It's a discrete distribution over, 100,000 tokens? More?
128,000 sometimes, and it's got that long tail.
Yes, the long tail.
Yeah.
Meaning most of your tokens have a probability that's basically 0 almost all the time, and that's exactly where the PPO ratio just completely falls apart.
The paper breaks it down into 2 big failure modes, right? The rare token trap and the common token collapse.
Yep. Let's start with the rare token trap, because I think this is the one that really kneecaps a model's ability to reason.
Okay, paint the picture for us.
So imagine your model is trying to solve a math problem. It's working through its chain of thought. Most of the probability is on common words, the is equals. But there's some really specific symbol, maybe a variable x or an operator, that has a tiny, tiny probability, like 10 to the minus 5.
So the model pretty much thinks it's just noise at that point.
Initially, yes. But then, through the RL process, the model gets a signal that says, hey, wait a second, that symbol is actually the key to the whole solution. The gradient wants to push its probability up. Let's say it pushes it to 10 to the minus 3.
Which is still incredibly small. We're talking 0.1%. In the grand scheme of the entire distribution, the policy has barely budged.
In terms of absolute probability mass, you're spot on. The change is negligible. But just look at what PPO sees. You're dividing 10 to the minus 3 by 10 to the minus 5.
That's a ratio of 100.
100. And PPO's standard clipping range is something like, 0.8 to 1.2? So PPO sees this ratio of 100 and just slams on the brakes. It clips the gradient entirely.
It says, whoa, that's way too big of a change. Shut it down.
Even though the actual change to the system was microscopic. It's because PPO only looks at the relative change, not the absolute one. So the model is structurally blocked from ever exploring those rare, crucial tokens.
Wow, that's a huge blind spot. So what about the other side of that coin, the common token collapse?
This one is arguably even worse for stability. So take a super common token, like the word the or the number 1. The model is incredibly confident about it. Let's say it has a probability of 0.99.
Okay, makes sense.
Now, imagine some update causes that probability to plummet down to 0.8.
That feels like a massive deal. You just lost almost 20% of your total confidence. That probability mass has to go somewhere. That's a huge redistribution.
It is a catastrophic shift in the model's behavior. But do the math for PPO. You divide 0.8 by 0.99, you get about 0.81.
Which is inside the clipping range.
Yep. PPO looks at that 20% collapse in confidence and just says, this is fine, nothing to see here.
So let me just get this straight. If I make a tiny, reasonable adjustment to a rare but important word, PPO freaks out and calls it instability. But if I completely shatter my model's confidence on a super common word, PPO just lets it slide.
That is the structural flaw in a nutshell. It's hypersensitive in the long tail where it shouldn't be, and it's completely blind at the head of the distribution, right where it needs to be the most careful.
And the authors connect this directly to things like mode collapse, or when a model just starts spitting out gibberish mid-training.
They show it really clearly. There are these scatter plots in the paper, figure 2, I think. They plot the ratio that PPO sees against the actual total variation, which is the real distance, and it's just a total mess. The ratio is pure noise for low probability tokens. It's not a useful signal at all.
Okay, so this brings us to DPCO, Divergence Proximal Policy Optimization. What are they actually doing differently?
They're essentially going back to first principles. The original idea behind trust region methods way back with CRPO, it was never really about ratios. It was always about limiting the KL divergence or the total variation between your old policy and the new one.
So they want to measure the actual distance the distribution moved, not just a noisy proxy?
Exactly. So they replace the clipping with a mask. And they say, we will only block an update if two specific things are true. First, the update has to be pushing the probability away from the trust region. And second, the actual divergence of the whole distribution has to be over some threshold.
So in our rare token example from before,
the ratio is 100, which PPO hated.
Yeah.
But the actual divergence, the amount of probability mass that moved, is tiny. So DPPO just says, go for it.
And for the common token collapse?
The ratio was fine, but the divergence is huge, a massive shift. So DPPO steps in and says, hold on, stop.
That sounds theoretically perfect, but I have to be the skeptic here for a second. Calculating KL divergence or total variation, that's not free. You have to sum over the entire vocabulary, right?
You do.
So if I have a $120,000 token vocabulary, and I have to do that giant sum at every single step of generation, isn't that just going to completely tank my training throughput?
Oh, it absolutely would. It'd be prohibitively expensive. You'd need a ridiculous amount of memory just to store the full distributions to compare them.
So what's the trick? How do they get around that?
This is the part of the paper that's probably the most clever and also the most debated. They use an approximation, a really aggressive one. They call it the binary approximation.
Binary as in 2, but we have, 100,000 options.
Yeah, think about it like this. The whole probability space is a pie chart. You have one slice of the pie, and that's the token you actually sampled, the one you chose. And then you have all the other 100,000 or so tiny little slivers.
Okay, I'm with you.
So if you make that sample token slice bigger, where does that extra probability mass have to come from?
From all the other slices.
If you make it smaller, where does that mass go?
To the other slices.
Exactly. The big insight here is that you don't actually need to track which of the other slices changed. You just need to know that mass moved from the selected bucket to the not selected bucket. So they just collapse the entire distribution into a simple Bernoulli trial. Select a token versus everything else.
That feels incredibly simplistic. Does that really capture enough of the signal? I mean, what if that probability mass moves to a really bad token that's hiding in that everything else bucket?
That's the exact question I had. But when you look at the math, total variation is the sum of absolute differences. And since the probabilities of everything in that everything else bucket are usually super low, the total shift is almost entirely dominated by the change in the one token you selected.
So by just watching the one token you care about, you're implicitly putting a leash on the behavior of everything else.
That's the idea. The paper shows that the total variation is approximately just the absolute difference in probability of the single sample token. It turns a 100,000 dimensional sum into one subtraction.
That is just ridiculously efficient. Did they check this against a more expensive method?
They did. They compared it to a top K approximation where they would explicitly track, say, the top 20 or 50 tokens. And the binary approximation performed almost identically. Turns out you don't need all that granular detail to keep things stable.
All right, so let's get to the consequences. They did this fantastic forensic analysis of what they call clipped tokens. They looked at which specific words PPO was constantly suppressing that DPPO was allowing.
This was my favorite part of the whole paper. Just validates this gut feeling that a lot of researchers have had for a while. PPO was systematically clipping the very tokens that are essential for reasoning.
So what was on the list?
A bunch of stuff. Mathematical symbols like 1, 4, the plus sign, the equal sign, logical connectors like thus, since, however. And this is the killer, the word wait. Yeah, wait. Think about how chain of thought works. The model is reasoning its way through a problem, and it realizes it made a mistake. So it generates the token wait to signal that it's about to pause or correct itself.
Like, wait, let me recheck that calculation.
Exactly. Now, under normal circumstances, wait is not a very probable token. It's a high entropy choice. It's a surprise.
So it starts out with a super low probability.
And then when the reinforcement learning tries to reward that behavior, to say, yes, that was a great correction, the probability ratio just spikes. And PPO sees that surprise and immediately clips it. It's basically telling the model, don't surprise me, just stick to the most probable path.
So PPO is actively discouraging the model from learning how to self-correct or how to follow complex logical steps just because those steps look like statistical outliers.
It's treating reasoning as if it were noise. But DPPO, because it's looking at the absolute mass, sees that the word wait still has a tiny total probability, so the divergence is low. It lets the update go through. It lets the model actually learn the language of logic.
This has to connect to those stability experiments they ran. The sanity check with DeepSeek R1 distill.
It does, yeah. They took a model that could already solve a set of math problems, and they just kept training it on those same problems.
The classic don't break what's already working test.
And PPO failed. Over time, it collapsed. The model actually got worse at solving the problems it already knew how to solve.
How does that even happen? If it already knows the answer, shouldn't RL just keep reinforcing that?
You'd think so. But the problem wasn't the correct answers. The collapse was caused by the negative samples.
The mistakes.
Right. Even a great model makes mistakes maybe 1% of the time. But when it does say it predicted 4 with 99% confidence when the right answer was 5, standard RL algorithms just react violently.
They see that extreme confidence on a wrong answer and they just try to smash it with a giant negative gradient.
They try to drive that probability to 0 in a single step. It's a massive update. It's like trying to perform brain surgery with a sledgehammer just to fix one tiny error.
And in doing so, you destroy all the weights that were supporting all the correct reasoning just to fix that one mistake.
It causes catastrophic forgetting. The paper shows it's less than 0.5% of the data, these huge negative spikes that cause the entire model to unravel.
And DPPO stops this.
The trust region kicks in and says, okay, that was a mistake. We need to lower the probability of 4, but we are not allowed to move the entire distribution more than our threshold, delta. It caps the damage. It turns that sledgehammer into a scalpel.
So it learns from the mistake without giving itself a lobotomy.
That's a perfect way to put it. It solves that training inference mismatch by letting the model survive its own errors.
I want to get into the weeds for a minute on the implementation side. There's a bit about anchor points that seems really important for anyone who's actually going to build this.
It is. And it's a detail that saves something like 25% of your compute time, which is not trivial when you're renting H100s by the hour.
So walk us through the anchor point idea.
Okay, so in any of these trust region methods, you're always comparing your current policy to some old policy. The big question is, which old policy?
Right. And usually in libraries like TRL or standard PPO code, you recompute the log probabilities of the old policy at every step to make sure your reference point is fresh.
You do. You compare your current training step against the policy for maybe just a few steps ago. They call it the recomputed on policy. The logic is that you want the most up-to-date comparison possible.
But this paper says that's wrong.
They argue it's actually mathematically unstable for LLMs because your reference point, the thing you're trying to stay close to, is also moving. You're trying to hit a drifting target.
So what's the right anchor?
The rollout policy. The literal, specific snapshot of the model that actually generated the data in the first place.
The version of the model that played the game, so to speak.
Exactly. You anchor to that. It's fixed. It doesn't drift. And the beautiful part is, because it's fixed, you don't need to run a whole extra forward pass to recalculate its probabilities during your optimization loop. You already have them from when you generated the text.
And that's the 25% speed up. You just skip an entire forward pass.
And you get better stability as a bonus because you aren't chasing a moving target. It's one of those rare cases where the cleaner math is also better engineering.
It's not often you see a paper that gives you better results and less compute at the same time. Usually you have to trade one for the other.
It really just highlights how much legacy baggage might be built into our standard practices. We've been doing these expensive things like recomputing log probs because we thought it was more accurate when it was actually hurting us.
So what about the final results? They ran this on Qwen 330B and some Llama models, right?
Yeah, on the AME 2024 and 2025 benchmarks. So really hard math problems.
And DPPO came out ahead of PPO, GRPO, CISPO, but I saw something interesting about the mixture of experts results.
This is super important for anyone using models like Qwen or DeepSeek. MoE models are inherently noisy. For the same input, the router might pick experts A and B one time and experts A and C the next.
And that routing noise can really mess with RL, can it? The policy is technically different every time.
It can. There's a common technique called rollout router replay, or R3, that forces the training loop to use the exact same experts that were used during the rollout, just to keep things consistent.
Did DPPO need that?
Nope. That's the really cool part.
Yeah.
DPPO performed well even without router replay. The divergence constraint is just fundamentally robust enough to handle the noise from the router switching experts around.
That's impressive. That suggests the method is actually more stable, not just getting lucky.
It means it's capturing the true underlying behavior of the distribution instead of overfitting to the specific path the computation took through the network.
Okay, so let's zoom out. The paper's message is pretty clear. Stop using ratio clipping. Start using divergence with a simple binary mask, and anchor your updates to the rollout policy.
And stop treating the long tail of your distribution like it's just statistical noise.
That brings me back to that clipped tokens list. Words like wait, therefore, since. You said earlier these are high entropy tokens. They're surprises.
Yeah. And in information theory, surprise is information.
So if standard PPO has been systematically suppressing these high entropy, high information tokens for the last, 3 or 4 years, what has that done to the personality or the creativity of the models we use every day?
It is a really provocative thought. We have some evidence from other research that those aha moments in reasoning, the little creative leaps, they often happen at points of high entropy. That's the moment the model considers something non-obvious.
And PPO steps in and says, nope, that's too weird, too risky, don't do it.
Exactly. We might have been systematically breeding the creativity out of our models by penalizing them every time they have a statistically interesting thought. We're training them to be safe, predictable, and average.
So DPPO isn't just about getting higher scores on math benchmarks. It's potentially about allowing models to think, stranger thoughts, without being punished for it.
It gives them a permission slip to go explore the long tail. And that's where all the interesting stuff usually lives.
I have a feeling we're going to see binary DPPO become the default in libraries like TRL very, very quickly.
Yeah.
The efficiency gains alone pretty much make it a no-brainer.
I'd have to agree. The implementation is simple, the math is cleaner, and it actually solves the catastrophic collapse problem. It's a pretty hard combination to argue against.
Well, for everyone out there training models, maybe it's time to check your clipping range, or maybe just throw out clipping entirely. The paper is Rethinking the Trust Region in LLM Reinforcement Learning. Definitely go check it out.
It is well worth the read.
Thanks for tuning in. We'll catch you on the next one.